This lesson deals with supplemental problem 221. You can find this problem in the ECE201 ebook in the Chapter 2 Supplemental Problem starting on page 19. I took a pair of commercial headphones that had a volume control on each of the headpieces and took some measurements and figured out there was a 500 ohm potentiometer in parallel with the headphone on both sides. The plug on a pair of headphones is configured usually this way, that the tip is the left channel and this ring over here is the right channel, and this sleeve is the common connection or ground. There's also an insulator between each of these. The terms tip, ring, and sleeve refer to the original landline telephone where connections were made by an operator. And I've shown here the left, the right, and the sleeve connection, which is the ground. Now when you plug this into a CD player, MP3 player, the left channel looks like a voltage source and it's being applied between this terminal L and ground. And likewise for the right channel, between this R and ground. What I like to do is plot the voltage across the headphone as a function of the rotation of the potentiometer. All right, what I've got here is a voltage divider. I'll represent the potentiometer as a percentage of the total pot, call this alpha times the 500 ohms, and then what's left over is 1 minus alpha times that 500 ohms, as we described in the Chapter 2 notes. So my voltage divider here on the left channel would be the 30 ohms in parallel with the alpha L times 500 divided by the sum of that plus the remainder of the pot, which is 1 minus alpha times 500. To be in parallel, we take the product over the sum. 30 times 500 times alpha over 30 plus 500 alpha would be the parallel combination, and the same is true in the denominator. I'm going to multiply numerator and denominator by 30 plus 500 alpha L. That's going to cancel this term. Going to cancel this term, and then we'll multiply this by the 30 plus 500 alpha L. I'll just kind of multiply this out. So I got 500 times 30, that's 15,000. I got 500 times 500, and that's 250,000. I'll take 1 times this, that's the 15K plus the 250K times alpha L. And then I've got alpha L times 15K. And then I've got alpha L again times 250K times alpha L. So I get an alpha L squared, and there's a minus sign in front of that. I do get two terms canceling here, this one, and I'm left with, put the highest power of alpha here, minus 250K times alpha sub L squared, and then I've got the 250K times alpha L plus the 15K. I've plotted this equation below, where on the y-axis I took the ratio of the output to the input, and on the y-axis I plotted alpha sub L. Take a look what that graph looks like. Looks like it's parabolic in shape, and it's probably coming from the fact that we have alpha sub L squared. Fairly linear over here, and then a rather rapid change for sub alpha. Let's take a look at some data points. So when alpha was equal to 0, I had the pot all the way to the bottom, basically shorting the output, I get nothing out. At a third of the rotation, I'm getting 0.0709. At half, 0.0967, which is about a tenth for the voltage divider. 2/3, 0.1417, 5/6, 0.2514, and then when the pot is all the way to the top, we have the output equal to the input. Now when I purchased these headphones, I noticed that when I was listening to them, as I rotated the pot, it seemed that the volume in the headpiece was linear with pot rotation. Now what you're hearing in the headpiece is really the sound pressure, and that's proportional to the power that's dissipated in the headpiece. That's going to go as the square of the voltage divided by the resistance of the headpiece. So this curve is actually going to be changing even more abruptly because we're going to square the output and divide by the resistance. So this is more like an exponentially increasing plot with rotation. Now it turns out your ear is logarithmic, and what that means is that when something sounds louder, we're talking about orders of magnitude of increase in the amount of power that's being dissipated in the headpiece. And that's what's happening here. We're seeing a factor of 1/10 to 1 for the voltage divider going from the half position to the full position. We're going to square the voltage and divide by the resistance to get the power. And this is supplemental problem 221.